Today we learned this linear time invariant system with the random inputs. So for this we define some basics. So you know this from the Fourier transform. If we take a Fourier transform of a time domain function, then we will get a function in a frequency domain. So if you have a random process like a wide sense stationary random process, and then you say this process is because it's a wide sense stationary process, so it has some correlation function Rx tau, and this Rx tau, if we take the function of time, and if we take its Fourier transform, then we will get power spectral density. And if you're like in your second or third semester, this you know how to calculate the Fourier transform of any function of t. So here tau actually t. So Rx tau is a function of t, and you are taking Fourier transform. So this is the kernel e raised to power minus 2 I pi f. F is in their second or third semester, it may be S, but here we are using F to represent its frequency domain. And this tau is the time domain, and we are integrating with respect to tau. So if we substitute after integrating the limit, we will get only function of F. Here J is actually imaginary, this I, square root of minus 1. So you can say either I or J. So the Fourier transform of the autocorrelation function of any wide sense stationary random process xt is known as the power spectral density, and it is denoted by S suffix capital X F. So, and if someone give you this power spectral density X S X S X F, then if you able to take inverse Fourier transform of this, then you will get the Rxt also, autocorrelation function, Rx tau also. So we'll see this. So the power spectral density is defined by this as suffix capital Xf. It is Fourier transform of the autocorrelation function of a wide sense stationary random process xt. And the Fourier transform of any function of t is given by this integration tau goes from minus infinity to plus infinity Rx tau e raised to power 2 I pi f tau d tau, and here this j is this square root of minus 1. Then if we take inverse Fourier transform of this Sxf, so here f then minus power something, minus 1 is actually representing inverse Fourier transform. This f raised to power minus 1 is actually inverse Fourier transform we are taking of this power spectral density Sxf. And you know how the inverse is defined, inverse Fourier is defined if this is Fourier transform kernel e raised to power minus 2 j pi f tau, then in inverse this minus should become plus, and then this Rx tau is replaced by the function Sxf, and we have to integrate with respect to the variable f. So, and you know that if we integrate this with respect to f and substitute the limit f equals to minus infinity and plus infinity, so whatever we get a function of tau, and that one is known as the Rx tau, that is the autocorrelation function for the random process xt. And some properties of this power spectral density is this, like autocorrelation function, it is also even function of f. Sxf minus f is equals to xsf, and it is always non-zero for all frequencies. Then we will see how we calculate this expected power. Earlier we know that the expected power in a random process xt, if the xt is wide sense stationary, then the expected power expectation of xt square is actually Rx0. and this is for wide sense stationary processes. So here this 0 actually tau. So we substituted this tau as 0, and we know that if we take the inverse Fourier transform of the power spectral density, here power spectral density is xf, and in the previous slide we know that the inverse Rx tau is actually inverse of the this frequency domain power spectral density xxf, and it is defined by this as xf e raised to power 2 j pi f tau df. So we'll use this formula. So Rx tau is equals to this, and then we replace that tau by 0, because if we replace the tau by 0, we will get the expected power in xt. So expected power xt square is equals to Rx tau, and this tau is actually 0, and we have substituted 0 here also from this result. Then so it means you can calculate your expected power in random process xt by directly integrating the power spectral density xf with respect to frequency f within the domain f goes to minus infinity to plus infinity. So the expected power of xt can be obtained like this. Either you use this Rx0, if someone has given you Rx tau, you substitute tau by 0, you will get the expected power. Or if someone have given you this power spectral density xf, you take its integration with respect to f within the domain minus infinity to plus infinity, whatever you get, that is expected power of in xt. So we'll see one example. So like one random process xt is there, and it is wide sensor stationary WSS, and we have its autocorrelation function, and autocorrelation function is defined like this: Rx tau equals to e raised to power minus a absolute of tau, and here a is a positive real number. It means a is strictly greater than 0, and find the power spectral density of xt. So power spectral density we have to calculate in this random process xt. So we'll take its Fourier transform of this Rx tau. We know that if xt is wide sense stationary process, we can calculate its power spectral density xf by taking Fourier transform of Rx tau. And the Fourier transform of Rx tau is defined by this Rx tau as it is. So this is Rx tau, this e raised to power minus a modulus tau, and this is the kernel of the Fourier transform, e raised to power minus 2j pi f tau and d tau, and you are integrating within the limit minus infinity to plus infinity. Here you know that this absolute of tau is having different definition in different domain. Like when this tau is lying between 0 to infinity, this absolute of tau will give you minus tau as a value, and then minus tau and minus a will become e raised to power a tau, and this kernel as it is d tau. Similarly, when this tau is ranging from 0 to infinity, the absolute tau is actually tau. So minus a tau e raised to power minus 2j pi f tau d tau. So to integrate this, we have to use this definition of absolute of tau, and you know that absolute of tau is equals to minus tau if tau is less than 0, and it is equals to tau if tau is greater than equals to 0. So we splitted this domain into two domain, and we have substituted the definition of absolute tau because it has two different definition in two different domain. And then we assemble this power of e here, e raised to power a tau minus 2j pi f tau. Here also e raised to power minus a tau minus 2j pi f tau d. And then you know the integration of this is equals to this one. And after substituting the lower and upper limit, you will get this result. And then by taking this LCM, you will get this. 2a square plus 4 pi square f square. Or if you remember your result from your second semester, like No, na, like Fourier transform of this function is this one. If you can remember this one, then you can also use directly. So here we have, if you are not able to remember those results, then we have to calculate by using the definition of Fourier transform. And the Rx tau is equals to e raised to power minus a absolute tau. Then its power spectral density is SXF 2a upon a square plus 4 pi f square. So this is the way you calculate your power spectral density. Now we have the concept of cross spectral density. So suppose you are having two random processes xt and yt, and they are jointly wide sense stationary processes. So you have to remember what is jointly wide sense stationary. It means xt and yt are itself wide sense stationary, and their cross correlation function is also function of the time difference, that is tau. So here it is given that xt and yt are jointly wide sense stationary process. Then we are able to define cross spectral density, and it is denoted by SXYF, and it is again the Fourier transform of the cross correlation function Rxy tau, and this Rxy tau is as it is, and this is the Fourier kernel and integrated within the domain minus infinity to plus infinity. Then we see the what is time invariant linear time invariant system, and with random inputs, like if you have some xt and you have one system with the impulse response ht, then if this signal goes to this system, then this is the output yt. So the linear time invariant system can be represented by impulse response, this one. More specifically, if xt is the input signal to the system and the output signal is yt, it can be written as this. So, and this is actually more specifically this line you can see, yt equals to ht convolution xt. So ht is the impulse response to this system, and xt is the signal, and this star is convolution. If you remember your Laplace transform, there is a theorem known as a convolution theorem. In Fourier transform also there is a theorem is known as convolution theorem. So this is actually convolution of two functions. One is ht, another one is xt, and this star is representing convolution. And you know that the convolution of two functions is defined like this. If ht star xt is h alpha, xt minus alpha d alpha, with this we are integrating within the domain minus infinity to plus infinity. And this convolution is also commutative, like xt star st also give the same result. So xt star st defined by this x alpha ht minus alpha d alpha. So the convolution of impulse response ht and the input signal will give you the output to this linear time invariant system. So the linear time invariant system output can be calculated by this ht star xt. Similarly, if you have discrete kind of random process, discrete time random process, then xn and hn, and then this is hn convolution with xn. So this is again when we have continuous, we integrate, and then when this discrete, then we sum. And this is actually this way we can write. Then, okay. So we consider a linear time invariant system with impulse response ht, and xt be a wide sense stationary random process. So this is given like xt is a wide sense stationary process. ht is the linear impulse response to a linear time invariant system. So if xt is the input to the system, then yt is output is also a random process. And more specifically, we can write like this. This we have already defined. Like if you have linear time invariant system with this impulse response ht, then the convolution of ht with xt will give you the output yt, and the convolution is defined by this h alpha xt minus alpha d alpha or x alpha ht minus alpha d alpha. So in any way you can define. Now that if there is a theorem, power spectral theorem, like here we have xt as a wide sense stationary random process and ht is the impulse response of a linear time invariant system, then this output is also wide sense stationary. We have to prove this one first. Second, we have to prove that this xt and yt are jointly wide sense stationary. So here our goal is to show that xt and yt are jointly wide sense stationary process. Let's first start by calculating the mean function of yt, because if you want to prove this, because xt is already given wide sense stationary, and to prove them xt and yt as jointly wide sense stationary, you have to prove first yt also as a wide sense stationary process, and then we have to prove their cross correlation function is also function of time difference, that is tau. So you calculate this mean first, for because first we show that this yt is wide sense stationary. So to show this yt is wide sense stationary, we have to find its mm, mean function and autocorrelation function, and mean function should be independent of time and autocorrelation function is a function of time difference. So you know that for any process yt, the mean function of yt is actually defined as expectation of yt. And expectation of yt, then we have substituted what is the value of yt. Value of yt is this minus infinity to plus infinity h alpha xt minus alpha d alpha. And then since we are integrating with respect to alpha, this e goes inside of this integration, and h alpha is independent of this time. So expectation of xt we have, and expectation of xt is actually mean function of the random process xt, and xt is given that wide sense stationary process. So the mean function of xt is constant, like for any t, in particular for t minus alpha also. So this expectation of xt minus alpha becomes mean function of xt mu x, because it is independent of time, as it is given that xt is a wide sense stationary process. And then this mu x comes outside of this integration, and we have this. And here there is no involvement of this time. So it means the mean function of yt is also independent of time. So one thing we have proved that mu yt is not a function of time. So we can write mu yt as mu y. Then we find the cross correlation function Rx tau T1 T2. So to calculate this T1 T2, we use the definition of cross correlation. So Rxy T1 T2 is actually expectation of Xt1 Y T2, because it is Xy T1 T2. So expectation of X T1 Y T2. And then you substitute the value of y. Y is actually this minus infinity to plus infinity h alpha xt2 minus alpha d alpha. Then since you are integrating with respect to alpha, so this xt go inside, and then this expectation also go inside, and this expectation goes on this expectation of t1 into expectation of t2 minus alpha d alpha. Again here this x is a wide sense stationary process, and t1 is a one time, and t2 minus alpha is another time. So it's like a auto correlation function of the random process xt, that is rx. One time is t1, another time is t2 minus alpha. And since it is wide sense stationary, so rx t1 comma t2 minus alpha is actually equal to the rx tau. Rx tau t1 minus this second time. So t1 minus t2 plus alpha. So here we can see that this again rx t1 minus t2 is a function of time difference. So we can say that this cross correlation function rx t1 t2 is again a function of time difference tau, like this. So you can write h alpha rx t tau plus alpha d alpha. Here we representing this T1 minus T2 as tau. Again, from here to here, we can write by using the definition of convolution. This is convolution symbol. This is star and this is star. So if we use the convolution definition, we will get this integral. So Rxy tau is equals to h tau star Rx minus of tau, or it is equals to h minus of tau star convolution Rx tau. Similarly, you have to calculate this Ry. So if you remember what is Ry, autocorrelation function of Ry T1 minus T2. That is, you have to use expectation of y T1 into y T2, and then you solve all these integration, and you will, in the end, you will arrive at this result. H tau convolution h of minus tau convolution Rx of tau. So here we see that this mean function of y is independent of time. One thing. Second is its autocorrelation function of y is again function of time difference. Third is the cross correlation function of r x and y is also function of time difference. So it means our xt and yt are jointly Whiteson's stationary processes. So here you can see that the theorem that we have already proved, that xt be a Whiteson's stationary random process, and it is given by this, where st is the input response to the system, then xt and yt are jointly Whiteson's stationary. Moreover, we are getting these results. So these results we remember. If xt is a Whiteson's stationary process, yt is a output given by this ht convolution xt, where st is the impulse response of a LTI system. Then xt and yt are jointly Whiteson's stationary, and this result we have to remember because we are going to use to solve the problem these results. Mu yt equals to mu y mu x into minus infinity to plus infinity h alpha d alpha. This we have obtained here. Here, this is the first result. Then cross correlation, it is the h of minus tau convolution rx of tau, or like this, because the convolution is defined like this, ht minus this alpha. So h of minus alpha rx t minus alpha d alpha. Then this autocorrelation function of y rx tau is equals to h tau convolution h of minus tau convolution rx of tau. Then so this is so we have already discussed this results. Power spectral density, and this inverse of power spectral density is the Rx tau, and then expected power expectation of xt square is equals to Rs0, and it is equals to minus infinity to plus infinity Sxf df. Then we have already solved this problem. So here you have full explanation of this, how we are integrating and substituting the limits, even though you can check the video that I already shared with you. There it is clearly visible. Then some basics of linear time invariant system. So a system is modeled by transformation. You know that if you have any transformation you apply on any input, you will get some output. And why we are calling them linear system, this is the linear property like this. If you have some real constant a1 ft plus a2 gt, gt is another signal, ft is one signal, then a1 ft plus a2 gt, and then you take transform t here, So the transform is equals to ATFT plus A2TFT. So this is actually linearity property for any transformation, even though you have learned this in your first semester when you learned this your vector spaces. So in vector spaces you have learned the linear transformation, and in the linear transformation actually this one, because this is the linearity condition. AFT plus A2GT is equals to A1 transform of FT plus A2 transform of GT. Now we talk about this linear time invariant system. Consider a linear system YT with this transformation. The system is called linear time invariant for any time t belongs to R. We have this, like whatever value of this transform of xt we are getting yt. So to get the transform of x at t minus t naught, that is at another time, we will get this by just substituting or replacing t by t minus t naught in the output yt. So if such a condition hold, then we will say that this is time invariant. So Dirac delta function can be represented as this: xs delta t minus s ds minus infinity to plus infinity. If xt is the input to the linear system yt, then you take transform of this, and this is actually x alpha delta t minus alpha, because this is the xt we defined in terms of the Dirac delta function, and then we have substituted here. Then again this t go inside, because this t is the transformation on the time variable this, and so x alpha remains outside. Then transform of delta t minus a is the response at a time t due to the shifted impulse delta t minus a. So if the system is time invariant like this, so same thing is proving like earlier, because whatever you are getting, you if you want to calculate for a different time, you just replace the time in the output. Therefore for the linear time invariant system we have this one: yt minus infinity to plus infinity x alpha ht minus alpha d alpha, that is convolution of impulse response st and the input xt, and the convolution is defined in terms of the integration. So the video is already shared. You can this is clearly visible to you in the video. This theorem we have already proved. Then this frequency domain analysis. So actually this is not okay. Do one thing, you go through the video and let me know now, because I recorded all this thing, and here it is actually h t e raised to power minus this Fourier transform kernel and dt. So like we can find this HF. HF is actually Fourier transform of HT. HT is the this impulse response to the linear transform LTI system. And if you take Fourier transform of the impulse response HT, you will get transfer function. Transfer function is known as capital HF. So the Fourier transform of impulse response ht is equals to capital HF, and capital HF is called the transfer function of the system. And you know how we define Fourier transform: minus infinity to plus infinity ht e raised to power 2 pi I f tau t dt. So in particular, if f is 0, then we have substituted 0 here, and it is tau, time is there. So we will see that this is because if f is 0, this whole thing is 0. So you can calculate h0 by directly integrating your impulse function within the time domain t goes to minus infinity to plus infinity. So the h0 you can directly calculate here. And if you remember the earlier result, this if your xt is a wide sense stationary process to a linear time invariant system with the impulse response ht. Then yt is also wide sense stationary random process with mean mu yt is equals to mu y, and this is the result, first result of the theorem, mu x minus infinity to plus infinity h alpha d alpha. So from here, this is stated red, blocked red, this you can see this and this are the same thing. Here the variable of integration is t, and here the variable of integration is alpha. So it means mu yt or mu y is equals to mu x into h0. So this is one result. This mu y equals to mu x into h0, because h0 is actually equal to this integral of the result of previous theorem, result of the previous theorem. And from here we can know that if we know the transfer function hf, then this integration is equals to h0. So if your random process xt is wide sense stationary, impulse response is ht, transfer function is capital hf, then the mean of the output mu y is equals to mu x into h0. So this is another result you have to remember. Then we calculate what is hg. Instead of f, we are trying to using g. So using g, then we know that it is again a Fourier transform of the impulse response ht. So instead of ht, we are writing the variable s. So it's a variable of integration. Either you can write t or s. So I write s, and this is the kernel of the Fourier transform. And then we put g equals to minus f here. So if you put g equals to minus f, in the left hand side I will get capital H of minus f, and in the right hand side this minus becomes plus, and I will get this one. And then if you put s equals to minus t, now in this right side of integration, you substitute the variable s by minus of t, then ds by minus dt. So you have this in the right side you will get t goes to minus infinity to plus infinity. This h is replaced by h of minus t, and then e raised to power minus, because here it is plus now. So to make it minus, we have used this kind of substitution, and we will get e raised to power minus 2 pi I ft dt. And here you can see that it is actually Fourier transform of the h of minus t, because h of t, here we are having ht only. If we are having kernel of Fourier transform, this e raised to power minus 2 pi I ft, and it is multiplied by this function h of minus t. So this is actually Fourier transform of h of minus, small h of minus t. So from here we can get that h of the transfer function minus of f is equals to Fourier transform of minus of h of minus t. So this is another result. Then we calculate the complex conjugate. So this above bar is representing the complex conjugate. So we take the complex conjugate on the both side. So we know that ft, this is a transfer function, and it is defined by this minus infinity to plus infinity ht e raised to power minus 2 pi I ft dt. So this is e raised to power minus 2 pi I ft is the kernel of the Fourier transform. Ht is the function, because we are taking Fourier transform of ht. And then this we have applied this bar, complex conjugate bar. So here we can see that there is only complex number I is available here in this exponent of e. So only the sign change here only, because this ht is a function of time or real function. So you will get this. So this minus is replaced by plus. But we have seen that if this minus is replaced by plus, and here the variable of integration is s, and here is the variable of integration of t, it means this thing equal to this thing. So finally this we can write h of minus f. So the complex conjugate of h of f is equals to h of minus of f. So this is another result. So here we have three results for transfer function. H of minus f is equals to Fourier transform of h of minus t, and it is also equals to complex conjugate of h of f. Okay, so these results we have to remember: this one, this one, this, and this. Next, we have this cross correlation function because xt is wide sense stationary, st is the LTI system impulse response, and y is the output. And in the theorem we have proved that y is also wide sense stationary, and x and y actually jointly wide sense stationary. We have proved this result. So, and in that result, in the theorem, the second result is this one, R x tau. If you remember, this is the theorem. Is here. Okay, this is the theorem. The second result is this one, R x tau, R x y tau, h of minus tau, R x tau, and it is defined. This is convolution, and explicitly, if you write the convolution, you will get this one. So we will see this how. So this is the second result, Rxy tau, which is h of minus tau star Rx tau. So this is the result of the theorem, second result. So we take Fourier transform both the side of it. So left hand side we will have this one, and the right hand side we have this one. So if you remember the result for convolution of Fourier transform, then you know that if you have two function like ht is another function, rx tau is this function, and if we have convolution of this, so the Fourier transform of the convolution of two function is equals to the product of their Fourier transform. This is the convolution theorem of Fourier transform you learned in your second or third semester. The convolution theorem of Fourier transform says that the Fourier transform of convolution of two functions is equals to the product of their Fourier transformation. So we have individually write their Fourier transform like this. And again here, what is this? F of h of minus tau, and it is f of rx tau. So you know that rx tau is actually autocorrelation function of x, and its Fourier transform is actually spectral density, power spectral density Sxf. So this Fourier transform of Rx tau is replaced by Sxf, and then Fourier transform of h of minus tau we have proved in the previous slide like this. Fourier transform of h of minus tau is equal to either h of minus f or h of f bar. So we can use any one. So here we have used h of minus f. So this Fourier transform of h of minus tau is equals to h of minus f, and Fourier transform of autocorrelation function of x is equals to the power spectral density. So you can calculate this Fourier transform of the cross correlation Rx tau is equals to this one. And we can define like this because this is actually cross spectral density. Today only we define the cross spectral density is equals to the Fourier transform of the Fourier transform of the cross correlation. So this is cross correlation, and we are taking Fourier transform. So the Fourier transform of cross correlation is equals to the cross spectral density. So from here you can write this is actually cross spectral density Sxyf, and this as it is. And this h of minus f is replaced by h of f bar also, because in the previous slide we have proved that h of minus f is equals to h of f bar. So this result we also remember because we use these to solve some problem. Third result is of the theorem is this one. This is actually we are having here the autocorrelation function of the output y. And the autocorrelation function of the output y can be or equal to this one, h of tau convolution h of minus tau convolution rx tau. And this is the third result of the theorem. This. So we have used the third result of the theorem, and we'll see. Now we take Fourier transform. Again, we use the property of the Fourier transform, which is a convolution of three functions. So the Fourier transform of the convolution of three function is equals to the product of their Fourier transformation. So like this we have, and then we know that Fourier transform of this unit impulse function h tau is equals to hf. This is transfer function. For minus tau, it is h of minus f, and this is actually autocorrelation function of x. So we get power spectral density x x f. So we will have this f r x y tau is equals to this one. So similarly, we can write this power spectral density in y is actually this s y f like this, because r x tau is equals to x x f. So r y tau is equals to s y f. So we have this result. This we have to remember. This blue result. S y f is equals to h of f into h of minus f into s x f. Or this because h of minus f is equals to the complex conjugate of h of f, like this. And even though this is like z into z bar, z into z bar, if z is complex number, it is equals to absolute of z square. So hf into hf bar can be written as hf bar absolute whole square, and this xxf as it is. So whatever the results we have derived here are this one. If xt is a wide sense stationary process, ht is the unit impulse response function to an LTI, then the output y is having this mean mu x plus 0. The transfer function h of this equals to this one. This SYF, the power spectral density in y is equals to this one in terms of the power spectral density of x into transfer function absolute square. And this cross spectral density is equals to this one. So this is the result problem. We will use all the above result to solve this problem. So here it is given that xt is a zero mean wide sense stationary process. So wide sense stationary it is given, zero mean it is given, and its autocorrelation function is also given here. Rx tau is equals to e raised to power minus tau, and xt is an input to an LTI system. So this is also given that xt is an input to the LTI system with transfer function. Transfer function is given to us instead of unit impulse function response ht, small ht. Instead of small st, we have provided here this transfer function hf like this 0 1 plus 4 pi square f square absolute of f less than 2. So if the frequency range in this domain it is this one, and otherwise this one, and yt is the output. So now you have to calculate mean of the random process yt. You have to calculate autocorrelation function of yt, and you have to find the power in the yt, expected power in the yt. So these three you have to calculate. So we use the first result to calculate mean. Since xt is wide sense stationary and xt is input to LTI system, so xt and yt are jointly wide sense stationary. We have already proved this theorem, and therefore yt is also wide sense stationary. So mu yt is actually mu y, and mu y equals to mu x into h0. This result we have already done today. This mu y equals to mu x into h0. So this we substitute. So hf is this one, and 0 lies in this one because mod of less than 2 means f is ranging from -2 to +2. So you put 0 here, you will get 1. But mu x is 0 because it is given here xt is a 0 mean. So 0 mean it means mu x is 0. So 0 into 1, you finally you get 0 as the mean of the output yt. Now second question is we have to calculate ry tau. So ry tau is actually autocorrelation function of output yt, and since yt is wide sense stationary, so if we take the this spectral density of y, if we take the inverse Fourier transform of the spectral density of y, we will get the Ry tau. So if somehow I know the what is the spectral power spectral density of y, that is SYF. If somehow I calculate this one, then I take inverse transform of this one and I will get the Ry tau, the autocorrelation function of y. And we have proved this result, this one, today only. SYF is equals to XXF absolute of HF square. So we'll use this result to calculate SYF because HF is already given. So we'll use this result XXF HF. So HF we have because this is given. Rx tau we have, but we don't have this SXF. This we don't have. So first what we do, we take the Fourier transform of this one so that we can have this SXF. HF is given. If somehow we calculate SXF by taking the Fourier transform of this one, and then we multiply, then we'll get SYF. And then we take inverse transform of SYF, we will get Ry. So this is actually, today only we have proved the one result, this one. This one. If we have some random process xt which is of white sense stationary with Rx tau equals to e raised to power minus a absolute of tau, if we have this kind of function, then its Fourier transform, that is power spectral density of xt, is equals to this one 2a upon a square 4 pi f square. So that is x f is actually 2a upon a square plus 4 pi square f square. But in the what problem we are dealing here, a is actually 1. So if a is actually 1, then it is like 2 upon 1 plus 4 pi square f square. So in the current problem, this e raised to power minus tau. So a is 1. So we substitute a equal to 1 in the previous result, like Fourier transform of e raised to power minus a absolute of tau is equals to 2a upon a square 4 pi square f square. So here what we do, we substitute a equal to 1, we will get 2 upon 1 plus 2 pi f whole square. So this is the one. Now we multiply this SFX to the HF. So this is HF is already there. So when f is lying other than this domain, it is 0. And we take a square of it. So a square of it means we will get 1 plus 4 pi square f square when f lies between minus 2 to plus 2 and otherwise it is 0. So we multiply this to this and this, because 1 plus 2 pi f whole square cancel out this and we will have only 2. So the product of these two functions will give you 2 when f is lies between minus 2 to 2 and otherwise it is 0 because hf is 0. So now you have SYF. Now you have to take its inverse Fourier transform to obtain Ry tau. So the Ry tau is equals to Fourier inverse transform of SYF, and the definition of SYF you have obtained is this one, and you are integrating within the domain minus infinity to plus infinity, you will have this. And then because minus 2 to 2 it has some definition too, otherwise it is 0, so you split it like this. And the integration of this again e raised to power 2 pi I f tau upon 2 pi I tau, and then you substitute lower and upper limit, you will get this one. And so this is the final result. Then the third result is to obtain the expected power in y. So the expected power in y means you have to substitute 0 ry0. Actually this is ry0, because if it is expected of xt square, it is rx0. So if you are calculating expected power in y, so it is ry0 and ry tau is already here. To obtain ry0, you take the limiting case of it. So if you take limit tau tends to 0, this upon this, you will get this thing is 1. So finally you will get 8 as the output. So this we will discuss in the next lecture. Okay, so I'm stopping here now, and the video of this is already shared, even the slide also. So we will meet again on Monday. We will meet again on Monday, and maybe on Tuesday we have test whatever covered till today. Okay. So attendance today I also given attendance to all of you. So if you have any question you can ask. Otherwise, you and I better to leave this meeting.